So I put all the other electrophysiology information in this last PowerPoint that I condensed to 20 slides. I recognize this could get us over the 15-minute chunk detention mark. I'm trying to keep these around 15, 20 minutes, around the maximum span of your attention. But on the bright side, you can pause me at any time if you need a break. So the learning objectives here to finish up the ePhys component are, I want you to be able to describe voltage-gated ion channels, compare and contrast IPSPs and EPSPs, describe how spatial and temporal summation dictate the postsynaptic potential, and describe the 7-step process that we are laying out here, that the book really lays out here. This is, this isn't the only way it can happen, but, it's a good, I think, example, this sort of 7-step process. And if you get this, I think you have the basis of, electrical conductance. When thinking about electrochemical signaling, it's, I think, fundamentally important to understand that there are 2 flavors of ion channels: voltage-gated and ion-gated ion channels. And it's also important to recognize that these are distinct from the metabotropic receptors, something that we'll get into very shortly. But metabotropic receptors are activated by a ligand binding to it. There are 7, typically 7 spanning units through the plasma membrane, and then they activate an effector, a G protein, 3-part effector protein that goes on to produce many intracellular signaling cascades. Ion channels are much faster, and of those, there are voltage and ligand-gated ion channels. These tend to be pentameric in nature. There's sort of a tunnel through the ion channel with 5 pillars that sort of make a whole. That can be, some of them are a little leakier than others, some of them are incredibly tight. But the keys to these are either voltage or a ligand, and these would be specific to one or the other. In the case of voltage-gated ion channels, there would be a pore or a site for a particular ion to activate. So, for example, if one were to be activated, it would be permeable to most likely one more selective ion. So if this sodium ion channel were to open, it would open exclusively, primarily for sodium, and then close when it is inactivated. Basic features of voltage-gated ion channels are that they open and close in response to a change in membrane potential. Once open, these channels recognize and selectively conduct specific ions. They are quite selective. These channels can close even while the membrane is still depolarized, which would produce what's known as inactivation. And these channels subserve a number of functions, including the generation and propagation of action potentials and the gating of calcium entry into synaptic terminals. Calcium, is thought to have a lot of sort of amplifying properties in neural communication. It is involved in many different things. It is also involved in the synthesis of endocannabinoids. You need, calcium is, one way that endocannabinoids like 2-arachidonoglycerol can be synthesized. Ligand-gated ion channels are the different flavor. Ligand-gated ion channels can be excitatory or inhibitory depending on their ion selectivity. But they would be activated by an actual ligand. And there are endogenous and exogenous ligands. Exogenous ligands mimic endogenous ligands. An example here, GABA, would be a primary, endogenous ligand. An exogenous ligand that acts like GABA would be a barbiturate, like what killed Marilyn Monroe. So GABA would be the primary inhibitory neurotransmitter in the central nervous system. At least in the adult, things are a little funnier early in development. And it's also worth pointing out that the receptor really determines that, the action of the receptor target. But in the adult brain, GABA A and GABA B receptors, GABA A is the ion channel, GABA B is the metabotropic G protein coupled receptor, both tend to produce inhibitory responses when activated by GABA. But GABA is the primary inhibitory neurotransmitter in the central nervous system and activates a class of ion channels called GABA A. These mediate the fast synaptic inhibitions, or IPSPs. By contrast, glutamate would be the primary excitatory neurotransmitter in the central nervous system and activates three classes of ion channels, AMPA, kainate, and NMDA, that mediate fast synaptic excitations, or EPSPs. Glutamate antagonists are a little more famous in pharmacology. Several of these are known to be ketamine. These tend to produce a sort of a dissociative state when you antagonize or oppose, glutamate action at the exogenous level, or the glutamate ion channels at the exogenous level. Obviously, I'm going to be using the terms EPSP and IPSP and postsynaptic potential, so it's probably pretty important that I explain these things a bit more in detail. Postsynaptic potentials are brief changes in resting potential or resting membrane potential. An excitatory postsynaptic potential would produce a small local depolarization, pushing the cell closer to threshold. And you can recall from 2220 that you must reach a level of threshold. Like every, there would be a threshold level, and every neuron is different. So I mean, like the 45, or whatever number you got in intro. This is going to vary a little bit from neural population to neural population. But there would be a threshold required for depolarization to occur, and you need enough buildup of EPSPs to get there without IPSPs preventing the EPSP from driving it up to fire. And it's almost always going to be, a summation event where you're going to have temporal and spatial summation from various inputs, and there would be multiple EPSPs and IPSPs competing. IPSPs, by contrast, produce small hyperpolarizations, pushing the cell further away from what required threshold for an action potential. IPSPs result from chloride ions entering the cell, making the inside more negative. So I love this little figure from your book. What you can see here is one neuron that is being recorded from two microelectrodes, and you can see the readout from two oscilloscopes there to the right. One microelectrode is positioned around ion channels that are receiving input from an excitatory presynaptic neuron that would be releasing, let's say, glutamate. And the blue would be, a inhibitory presynaptic neuron, let's say a GABA neuron. So you have the glutamate neuron there firing, and you can see that fire detected from another microelectrode placed in that excitatory presynaptic neuron. Right after that burst fires, you can see a lagging EPSP in the postsynaptic neuron. And by lagging, I'm talking about milliseconds here. This is very rapid, but it's still obviously behind the presynaptic impulse. On the other side, you have your GABA neuron that would be firing. And when this is excited and fires, it releases GABA, which would then activate inhibitory GABA receptors on the postsynaptic side, which would result in an IPSP. So in this case, if you have a net IPSP and one net IPSP and one net EPSP, most likely that would not be sufficient to alter the firing rate of the postsynaptic neuron. It's how these things build up through spatial and temporal summation. It's really important for how they fire and for behavior, learning, emotion, these sorts of things. These would be determined more through activation of microcircuits and really competing microcircuits. So when you for the big picture of synaptic plasticity, think about how this would occur. Through learning, through experience, you might find that you reinforce one action that would occur over and over and over to provide you with an advantageous outcome. And for that to occur and sort of to begin to develop more habitually or in an automated fashion, you would need quite a bit of changes in basically synaptic remodeling. So what would tend to happen there is there would be a shift in input, and that shift in input would result in changes in what's known as dendritic spining. So what happens is you have these little things called philopodia, which are like little exploratory arms reaching off of the dendrites that would go out and sort of look for new hot stuff that might be better than what's currently going on. And when it finds something, this increase in input, it might bolster the postsynaptic response by adding, let's say, AMPA receptors or other ionic receptors around the area. And this would strengthen the particular synapse in a way that might reinforce whatever action or emotion is associated with this sort of anatomical or cytoarchitectural changes. Neurons perform information processing to integrate these synaptic inputs. Before anything was strengthened, you first have to do the initial processing. So here, a postsynaptic neuron will fire an action potential if a depolarization that exceeds threshold reaches its axon hillock. For this to occur, you would have to have summation of a lot of EPSPs over IPSPs. So this little three-part animation here shows the role of excitation and inhibition and their integration at the axon hillock. It shows this very nice visually. So if you have a lot of excitatory input, that would of course drive you toward an action potential. In contrast, inhibitory input or increased inhibitory input will drive you away from an action potential. Thus, your end result is really something more like this, where you have a lot of excitatory and inhibitory input that would be competing. And really based on learning experience, changes in dendritic spining on the postsynaptic side and presynaptic input on the presynaptic side, you will determine, that will lead to determine whether or not you see sufficient EPSP summation at the level of the axon hillock that would be necessary for an action potential or for the cell to burst fire. Thus, it's really the summation of these EPSPs and IPSPs that's so critical for information processing. There are spatial and temporal forms of summation. Spatial summation is the summing of potentials that come from different parts of the cell. If the overall sum of EPSPs and IPSPs can depolarize the cell of the axon hillock, an action potential will occur. The figure that we just saw would be a good example of spatial summation. Here's another good illustration of spatial summation. So you would have three distinct inputs that are all excitatory in nature, acting on the neuron, or the postsynaptic neuron. This would drive so you can see the little readout of the oscilloscope on the right there. So, three different excitatory inputs might be sufficient in this case to pass the level of the threshold needed for the action potential to occur. Temporal summation, on the other hand, is the summing of potentials that arrive at the axon hillock at different times. The closer together in time that they arrive, the greater the summation and possibility of an action potential. So here is an example of temporal summation that looks very similar to the last figure we saw for spatial summation. The difference here is rather than excitatory input arriving from three different spatial locations, you're getting a series of bursting inputs from one excitatory input here. So there's going to be one glutamate fiber that's just firing repeatedly from one source And this would be a form of temporal summation that would sort of build on itself from the one spatial input.
Postsynaptic potentials that are caused by neurotransmitter chemicals can be either depolarizing, often but not always resulting in an excitatory postsynaptic potential, or EPSP, or hyperpolarizing, resulting in an inhibitory postsynaptic potential, or IPSP. Postsynaptic potentials generally move passively along the dendritic membrane, gradually becoming smaller as they spread. Therefore, the postsynaptic potentials from more distant synapses will decay more than PSPs from synapses closer to the integration zone at the axon hillock. The postsynaptic potentials produced at most synapses are usually well below the threshold for generating postsynaptic action potentials. How then can synapses transmit information if their postsynaptic potentials are subthreshold? Suppose that two excitatory endings are activated, causing local depolarizations of the cell body. Taken alone, neither would be sufficient to trigger an action potential, but when combined, the two depolarizations sum to depolarize the membrane in the hillock region to threshold. When inhibitory synapses are active, the membrane potential tends to be stabilized below threshold because they induce hyperpolarizations, or subthreshold depolarizations, that cannot reach threshold. These postsynaptic effects also spread passively, dissipating as they travel. Because some potentials excite and others inhibit the hillock, these effects partially cancel out each other. Thus, the net effect is the difference between the two. The neuron subtracts the IPSPs from the EPSPs. Postsynaptic effects that are not absolutely simultaneous can also be summed, because the postsynaptic potentials last a few milliseconds before fading away. The closer they are in time, the greater is the overlap, and the more complete is the summation, which in this case is called temporal summation. The summation of potentials originating from different physical locations across the cell body is called spatial summation. Only if the overall sum of all the potentials, both EPSPs and IPSPs, is sufficient to depolarize the cell to threshold at the axon hillock is an action potential triggered.
So that, I think, is a great video reinforcing the ideas of spatial and temporal summation, while also reinforcing concepts about the oscilloscope and how you actually record and detect these things. But the final thing that I want to leave you with here, when we think of electrical transmission, is a good solid example. So here, I just want to give you a 7-sequence step of transmission that is really based on your book. Keep in mind that this isn't one size fits all. This isn't the only way that it occurs in the nervous system, but this is a good, I think, standard example of what this looks like. So the sequence of transmission events that I want you to be familiar with is as follows. The action potential would travel down the axon to the axon terminal. The voltage-gated calcium channels would then open, resulting in calcium ions entering the cell. The synaptic vesicles will then fuse with the membrane and release the transmitter out into the synaptic cleft. Then the transmitters cross the cleft and bind to the postsynaptic receptors to cause either an EPSP or an IPSP. The EPSPs or IPSPs spread toward the postsynaptic axon hillock. Then the transmitter is inactivated, sometimes by enzymatic degradation, or removed by transporter reuptake, meaning that its action would be brief. Diffusion also can occur there. The transmitters may also activate presynaptic autoreceptors, which would decrease the release of the neurotransmitter. Presynaptic autoreceptors are typically metabotropic. That means G protein coupled receptors. One that's commonly talked about is the 5-HT1A receptor, which is the serotonin autoreceptor. This inhibits serotonin release. In general, increasing serotonin levels produces a great deal of anxiety. It's anxiogenic. So, it would be potentially pharmacotherapeutic to activate serotonin 5-HT1A receptors, in the case of an anxiety episode, because that would reduce the amount of serotonin if said anxiety is associated with increased serotonin. This is also thought to be one of the rules through which SSRIs work and are effective in treating anxiety disorders. They are still what is most prescribed and recommended in psychiatric medicine for the treatment of anxiety. This is something we can talk about a little further and definitely in detail in my drugs class. But interestingly, the 5-HT1A receptor has been shown to be activated by cannabidiol pretty recently. If this is true and it holds up, it might explain why cannabidiol might reduce anxiety.
Communication between neurons and communication between neurons and muscle occurs at specialized junctions called synapses. The most common type of synapse is the chemical synapse. Here, we examine the events that take place at the neuromuscular junction, a chemical synapse using the neurotransmitter acetylcholine. Synaptic transmission begins when the nerve impulse reaches the presynaptic axon terminal. Depolarization of the presynaptic membrane initiates the sequence of events leading to transmitter release and activation of receptors on the postsynaptic membrane. Shown here are the principal molecules and organelles necessary for release of neurotransmitter. Synaptic vesicles exist in distinct pools, either tethered to the cytoskeleton in a reserve pool or free in the cytoplasm. Some of the free vesicles make their way to the plasma membrane and dock as a series of priming reactions prepares the vesicular and plasma membranes for fusion. The membranes of the synaptic vesicles are drawn together via protein complexes, collectively called snares, that are expressed on the vesicle and presynaptic membrane. When the axon terminal is depolarized, voltage-gated calcium channels open, and calcium ions rush into the axon terminal. Some of the calcium ions bind to a protein on the synaptic vesicle membrane called synaptotagmin. When calcium binds to synaptotagmin on the synaptic vesicles nearest the active zone, the vesicles are drawn even closer to the presynaptic membrane. The vesicles fuse with the axon terminal membrane and release their transmitter cargo into the synaptic cleft. Some of the transmitter molecules bind to special receptor molecules in the postsynaptic membrane. The response of the postsynaptic cell, either excitation or inhibition, depends upon the particular neurotransmitter and receptor combination. For example, the receptor for acetylcholine is permeable to sodium. After binding acetylcholine, the channel opens and sodium ions enter the postsynaptic cell, thereby generating an excitatory postsynaptic response. Transmitters are inactivated or removed rapidly from the synaptic cleft so that transmission is brief and accurately follows the presynaptic input signal. For acetylcholine, an enzyme in the synaptic cleft, acetylcholinesterase, breaks down acetylcholine into choline and acetate. The release of transmitter from the receptors causes the channels to close. Not all transmitters are broken down by enzymes in the synaptic cleft. Many transmitters are rapidly cleared from the synaptic cleft by being taken up into the presynaptic terminal by special proteins called transporters. This process is known as reuptake. Reuptake not only cuts off the synaptic activity promptly, but also allows the terminal to recycle transmitter molecules. The membrane needed for creating synaptic vesicles is also recycled via endocytosis of the presynaptic membrane. The recycled vesicles are refilled with neurotransmitter molecules and are ready for another round of synaptic transmission.